So when looking at the electric field, we put positive test charges next to a source charge and then looked at how much force they experienced. So we can also look at how much electric potential energy the source charge and the test charge will have. So if we put a test charge Q next to a source charge, then the system will have an electric potential energy given by this equation. And again, if we increase the charge on the source charge, then the electric potential energy will also increase by the same amount. But the ratio of the electric potential energy divided by the test charge will stay the same as long as we're talking about the same source charge. So just like how the E field describes the ratio of the force over the test charge, the electric potential is the ratio of the electric potential energy divided by the test charge. And so the magnitude of the electric potential is a scalar quantity, not a vector, because energy is scalar. So the electric potential at any point, a distance from the source charge, will be k times the source charge divided by Again, it does not depend on the test charge. So, if we put a charged object of charge q in a position with a electric potential V, then it will have Q times V of electric potential energy. And the unit of electric potential is joules per coulomb, which is called the volt. And electric potential depends on where you choose the zero level, because electric potential energy depends on where you choose the zero level. Much like, when we use the equation for gravitational potential energy, mgh, we have to choose where h equals 0. And so for electric potential and electric potential energy, the zero level is usually when the charges are an infinite distance apart, or very far. So a lot of the time we are only concerned with the difference in potential between 2 points, which is called the potential difference, or this delta V. And positively charged objects will accelerate from areas of high potential to low potential. Because if an area has a higher potential, that means it's closer to a positive source charge. And we know that positive charges will repel. And negatively charged objects do the opposite. They like to go from low potential areas to high potential areas, because they're attracted to those positive source charges. So let's say we have a region where the potential difference is 40,000 volts. So that means this final point is 40,000 volts higher than this initial point. So if we have an electron that starts at rest and it accelerates to this region, because negatively charged objects accelerate from low to high potential, then how fast will it be moving at the end? So when an object moves through a potential difference, then the change in electric potential energy will be equal to the potential difference times its charge. We just got that from rearranging the definition of electric potential. So we plug in the charge of an electron and the voltage difference to get that we find that the change in energy is negative. So when negatively charged objects move from low to high potential, they lose energy. And that means positive charged objects do the opposite. when they move from high to low potential, they lose energy. So this potential energy that it lost was converted into kinetic energy. So we set the positive of this equal to 1/2 mv squared, and plugging in the mass of an electron, we can solve for its velocity. So just like how we used E-field lines to represent the electric field, we use equipotential surfaces to represent the electric potential in a region. So there are these dotted circles, and in each of these equipotential surfaces, the electric potential has the same value. So at every point along this circle, the potential is the same, because it's the same distance from the source charge. And so if we draw the E-field lines on top of this diagram, the E-field lines will always be perpendicular to the equipotential surfaces. And the more close together the equipotential surfaces are, that means the electric potential is changing faster. So the E field and the electric potential are related by this equation. So the electric field in the x direction is equal to negative delta V over delta x. And there's another equation that's for the electric field in the y direction and the z direction. So this means that the rate of change of the electric potential with respect to the distance is the negative of the electric field. So if an electric field is positive between 2 points, that means the rate of change of the electric potential along that distance will be negative, because the electric field points in the direction of decreasing electric potential. The electric potential at this point is higher than at this point along the E field line, because they're moving further away from the source charge. And the larger the E field, the more rapidly the electric potential changes. So that the bigger this rate of change of the electric potential will be. So the last thing we're going to look at is properties of conductors. And in electrostatic conditions, any excess charge that a conductor has to sit on the surface, not inside it. So you can see that all these negative charges are on top of the conducting sphere instead of over here. And the electric field inside a conductor is always 0, because if it was not 0, then the charged objects will experience a force and move around. And if they're moving, then it's not electrostatic anymore. So inside a conductor, the electric field is 0 and the electric potential is constant. So this whole conductor is a big equipotential surface.